Welcome back to another lesson in MCR3U. Today we'll be looking at investigating the rational function. So when we look at rational expressions, we see that, again, a polynomial function is a function of the form f of x is equal to a subscript n x to the power n plus a subscript n minus 1 x to the power of n minus 1 plus a to the subscript n minus 1 x to the power of n minus 2, so on and so forth, right, until we get to, again, a subscript 1 x plus, and then a subscript 0. And so an example, again, of one of these polynomial functions would be f of x is equal to x squared plus 3x plus 2. And so again, here where a subscript n, a subscript n minus 1, a subscript n minus 2, all the way to a subscript 1, and a subscript 0 are real numbers, and n is also a whole number. So plenty of examples of polynomial functions. F of x is equal to x squared plus 3x plus 2 is just one example. If we're simply looking at a polynomial expression, so polynomial expression is the right-hand side of a given function. So here, the expression would be x squared plus 3x plus 2. A rational function, so a rational function is a function in the form of f of x is equal to p of x over q of x, where p of x and q of x are polynomials. So here, an example would be f of x is equal to 3x squared plus 5x plus 2 over 2x squared plus 5x. So again, both p of x and q of x are polynomials, and then a rational expression would simply just be the right-hand side of the given function. So here, that would just be 3x squared plus 5x plus 2 over 2x squared plus 5x. So now what we're going to do is we're going to explore a little bit in terms of the properties of this particular function. F of x is equal to 1 over x. F of x is equal to 1 over x is our parent function for this rational function here. So here it says graph the function y is equal to 1 over x by completing the following table of values. So here we have values of -2, -1, -1 over 2, so on and so forth for x. If we sub those in, the corresponding y values will be -0.5, -1, -2, -3, -4, 4, 3, 2, 1, and 0.5. And here, you notice that there's no 0, because if we subbed in x is equal to 0 into the function y is equal to 1 over x, we get 1 over 0, which means that it would be undefined. So again, here we see that, again, x cannot be 0, and x cannot be 0, as the denominators of 0, denominators of 0 would make the expression or equation undefined. And what you'll also notice is that there's no value of x, then therefore that would make y is equal to 0. So here we write there is no value of x, that would make y equal to 0. Okay, so here we have, again, what are called asymptotes. So we have an asymptote at x is equal to 0 and y is equal to 0. So we'll note that by a dotted line here, and we'll explore more about asymptotes later as well. So here we have two asymptotes. Again, this is when x is equal to 0 and also when y is equal to 0. And again, these are called asymptotes. And so again, let's sub some of these values in. So here, if we have -2, we have -0.5, -1, -1, -1/2, -2, -1/4, and -4. So it looks something like this. And then we have 1/4 and 4. We have 1/3 and 3. We have 1/2 and 2. We have 1 and 1. And then finally 2 and 0.5. So it looks something like this. And here, what we'll notice is that, again, these functions here will approach our x is equal to 0 and y is equal to 0, but are not touching those. And that is one of the distinguishing features of an asymptote. And so here it asks us, why does the graph of y is equal to 1/x appear in only the first and the third quadrants? And so here, let's just label our quadrants. Remember, it starts from top right, then it goes counterclockwise. So that's quadrant 1, quadrant 2, quadrant 3, and quadrant 4. So here we see that again, it only shows up in quadrant 1 and quadrant 3. And so here, why does it only appear in the first and third quadrants? Here we see if we take our function and we do 1 divided by positive x, each time we do that, the answer will always give us a positive y value. So therefore, we have positive x, positive y, which means that it will appear in quadrant number 1. And same thing, if we take 1 divided by a negative x value, each time it'll give us a negative y value. So negative x, negative y, that will always appear in quadrant number 3. Okay, so again, when we look back at our asymptotes as well, let's just define that. So an asymptote it's a line, so it's a straight line that a curve approaches. More and more closely, but never touches. So a line that a curve approaches more and more closely but never touches. And here we saw that again, that was x is equal to 0 and y is equal to 0. And again, we represent that using, again, dashed lines. Okay, and so here, again, we saw that we had two types of asymptotes. We had the vertical asymptote, that was the vertical line, which was x is equal to 0. And we also had a horizontal asymptote, which was the horizontal line, which was y is equal to 0. Okay, so again, we use VA and HA to represent, again, our vertical and horizontal asymptote. As well here, therefore, when we're indicating our domain for our parent function, our domain and range, again, we see that our domain is x as an element of real numbers, but we also have to include a restriction, x cannot be equal to 0. And same thing for our range, y is an element of real numbers. But here, again, y cannot be equal to 0. Okay, so continuing our exploration, we're going to complete the following table of values for the function y is equal to 1 over x. So here we see that x has 0.001, 0.01, 0.1, so on and so forth. You see here that x is increasing from left to right. So when we sub that in, we get values of 1,000, 100, 10, 1, 0.1, 0.01, and 0.001. And so you see that as x is increasing, y here is decreasing. So here, as x increases in value, the y values are decreasing. And then again, if you flip it the other way, again, as x is decreasing, then the y values would be increasing. So here we see that as x increases, then the y values decrease. And so here, will y ever reach 0? And so we can say that no, as x increases, as x increases, y is smaller and smaller value. So y is a smaller and smaller value. Again, but will never reach 0. So here again, if we do 1 over positive infinity, a very, very large number, y will just give us a very small number. And then as x decreases in value, so if we go the opposite direction, so as x decreases, our y values will increase. Okay, and so will y ever reach a maximum? So here as well. So no, again, as x is approaching 0, so as x is approaching 0, y is greater. But again, since x cannot be equal to 0, y would be undefined. Okay, so now let's complete the table of values for, again, the function y is equal to 1 over x. But now we see that the values of x are negative. Okay, so here we see that if we sub those values in, we'll get negative 1,000, negative 100, negative 10, negative 1, negative 0.1, negative 0.01, and negative 0.001. And so what happens now, as x decreases in value, what happens to the y value is, again, x decreases, y will increase. And then same as the first question, again, will y ever reach 0? So same as question 1. And then as x increases in value, then what happens to the y value? Then y will decrease. And then will y ever reach a minimum? So in this situation, again, same thing, because as it approaches 0, again, it gets smaller and smaller, but since x cannot be equal to 0, y would still be undefined. So here, again, same as question 1 in terms of the reasoning. Okay, so again, mentioning the asymptote, again, a line that a curve approaches more and more closely is called an asymptote. The word asymptote comes from the Greek word asymptotos, which means, again, not meeting. Okay, so again, here, again, just reiterating what we stated earlier. Again, the vertical line x is equal to 0 is a vertical asymptote of the graph y is equal to 1 over x. The function 1 over x is not defined when x is equal to 0 because the denominator cannot equal 0. Since there's a break in the graph of y is equal to 1 over x at x is equal to 0, we can say that the graph is discontinuous at x is equal to 0, which means that it doesn't flow in one motion, really, in terms of the function. So here we want to graph the function y is equal to x on the same set of axes as the graph y is equal to 1 over x. Describe the relationship between, again, the graphs of y is equal to 1 over x and y is equal to x. So here we have a graph on the right. So let's graph, again, our function of y is equal to 1 over x first. So kind of look something like this. And same as when we graphed it at the top as well. And that one's in quadrant 1. And then in quadrant 2, it will look, or sorry, in quadrant 3, it'll look something like this. Okay, so that's, again, our function, and we'll label that f of x is equal to 1 over x. And then we also have our line y is equal to x. And just plotting a couple points here. We'll draw that line right through. And that's our graph. We'll label that g of x is equal to x. Again, y is equal to x. Okay, so let's look at these characteristics and then we'll compare again the y is equal to 1 over x and y is equal to x. Right, so here, if we look at our domain, again, for y is equal to x, we have, again, x is an element of real numbers. For our range, we also have y is an element of real numbers. Again, when is y is equal to x positive, we see that y is equal to x is positive when x is greater than 0. When is y is equal to x negative? That's whenever x is less than 0. And then, so here we look at the intervals of increase. So what the intervals of increase are is we can describe it. So as x increases, what happens to y values? Okay, so as x increases, what is happening to y values? And if those are also increasing, that's where the intervals of increase are. If the y values are decreasing when the x values are increasing, then that's the intervals of decrease. So here we see that our intervals of increase are x as an element of real numbers. Anytime that the x values increase, the y values are increasing. Here we see that the intervals of decrease, there is none. Vertical asymptotes for y is equal to x, there's none. Horizontal asymptotes, there's also none. And then quadrants, in which quadrant does the graph begin and finish? So here we see that for y is equal to x, it starts at quadrant number 3, and it ends at quadrant 1. Okay, so let's look at y is equal to 1 over x. Our domain, similar to, again, y is equal to x. However, this time we have, again, an asymptote. So again, x is element of real numbers, but again, x cannot be equal to 0. Okay, so here we have x is element of real numbers, but again, x cannot be with 0. For our range, same thing. Same range again, but you have to note the asymptotes, then y cannot be equal to 0. When we look at our positive interval, we notice that it's actually the same. So here, when we look at our positive intervals, we notice that they're actually the same as y is equal to x. So we see that here, when x is greater than 0. If we look at our graph, we see that all the positive values, again, are when x is greater than 0. We see the same thing here. X is less than 0. Again, for our negative intervals, all the negative values, again, for the function are, again, when x is less than 0. If we look at the intervals of increase, so here if we look at our graph, f of x is equal to 1 over x, as the x values increase, is there any point where the y values increase as well? And there isn't. So we can say none. So then our intervals of decrease, we see that, again, when the x values increase, the y values decrease at all points except for, again, our asymptote. So here we see that again, it's x is an element of real numbers, but x cannot be equal to 0. So we notice is that the intervals of increase and decrease actually flip here, again, but including the asymptote as well. Again, we have our vertical asymptotes, or asymptote at x is equal to 0, and we have our horizontal asymptote at y is equal to 0. And here we see that the quadrants, it actually begins at the same quadrant and ends in the same quadrant. So again, it starts at quadrant 3 and ends at quadrant number 1. Okay, so here again we see quite a bit of similarities in terms of the graph. Y is equal to x, and y is equal to 1 over x, 1 over x in terms of its characteristics.